thanks for joining us. It's my pleasure to introduce Dr. Alessandro Crimi, who has a PhD in machine learning applied to medical imaging from the University of Copenhagen, and he's also got an MBA in health management from the University of Basel. He previously worked at the French Institute for Research in Computer Science and also in Technical School of Switzerland and Italian Institute for Technology and University Hospital of Zurich. So a long list. He's been involved in global health projects in sub-Saharan Africa as well. So kind of a nice diverse background there, lots of experience. And today he's going to be talking to us about AI approaches focused on stroke imaging. So, Alessandro, I'll let you take it away from here. Thanks for being with us today.
Yeah, thank you for having me. I used to attend a lot of these meetings before Corona. Then I got busy, so I didn't follow anymore neither the Slack channel nor the presentation, but I used to attend most of them. Yeah.
Welcome back.
Yeah. And then, as I say, this is more. I will go through some works we did about effective connectivity, and mostly about this latest one that we published now in IEEE Access. But I hope we can have a more interactive conversation if someone wants to complain about effective connectivity, because I know many people complain that it doesn't exist or have their own view or whatever. So I'm actually open-minded if someone wants to complain about it, not just listen to my talk. Yeah, and this talk was mostly, as I said, about this latest paper we had. That is more overall framework we had about effective connectivity for stroke patients, both because we have our, let's say, new way right now, our latest, because we tried different things in the past about effective connectivity based on reservoir computing, plus some discussions more focused on stroke. So these are the two, they will be two key takeaways that I will share with you at the end, but there are two main blocks in this talk. I assume everybody attending this kind of talks are familiar with structured connectivity, functional connectivity, but just in case this is the first talk. So structured connectivity, when we say structured connectivity, we refer to the physical connections, like, for example, axonal fiber bundles, like from one brain region to another. Functional connectivity is generally the correlation, co-activation of big brain areas. And when we say effective connectivity, is we consider the amount of the influence that one brain region might have after some time point in another region. So it's not just temporal correlation. So in fact, there are many definitions. Some are strict, more say closer to what is temporal correlation. Some are more deeper, trying to understand if there are real causal effects of some activity in some one region or in another region. And just to remind, the usual story, what the difference between correlation and causality. There was this story of that's been published some years ago. I don't know. Have you seen already this? I don't know.
No.
So it's a plot, like say, showing that there is a correlation between chocolate consumption and people, chocolate consumption per capita in a country and people winning the Nobel Prize in the country. And it seems like more chocolate you eat, more Nobel Prize you have. Although this is like a spurious correlation, because what's going on is actually that rich country, people buy more stuff, of course, then they also buy more chocolate. So they have a higher chocolate consumption, and also they pay more scientists, so they attract more high-profile people that then might be Nobel laureates. So the cause is not that you eat chocolate and you win the Nobel Prize, but that there is a high GDP per capita in the country. So then you get both these things. So this to mention that if it's already complicated in something simple like this, so if you imagine in the brain signal, things get even more complicated. So in fact, we had a series of ways that are, let's say, used to define effective connectivity. So the simplest, I would say, is Granger causality. Then there is convergent cross mapping, transfer entropy. Of course, there was the dynamical causal model that was more like a validation of a model, not really a causal discovery. And there is none of them, at least in my experience, none of them can give a definitive answer. So some are stricter, some are more relaxed, but some are more computationally heavy, some are all these things. So there are pros and cons. Generally, what everybody is doing is, because assuming you're not using a model validation with dynamical causal model from Princeton, is Granger causality. And the idea is that you have two steps to define the real direction of the cause and effect between two regions. So of course, we use some kind of functional data like either fMRI or EEG or MEG or something else. And first of all, we need to have some temporal element, like that if you have some activity, let's say in the brain region X, after some time point, there is some activity in brain region Y. And this is the first step. Of course, if it was just this, there will be just temporal correlation. But then what we do is that we try to predict the time series afterwards, and we see if there is an added value considering both time series to predict one of them. Because if there is just this effect here, that there is just a temporal correlation, if you just can predict later on the time series and no statistical added value of the other time series, if the reconstruction of the forecast is better using two or more time series, then there is an actual cause and effect relationship. This is in short what Granger causality is about. Obviously, it's not the best definition of causality. Many people will complain about it because it's just, in the end, it's some fancy way of you looking at temporal correlation, but it's like a simplest way and is actually computationally not much demanding, so it's used a lot. I also like it because even if it's not ideal, I mean, it's quite simple and you can make it brain-wide very easily. One thing that I did some time ago, even though it was published in 2029, was actually a very, very old paper. So I tried to merge the fact that there is this cause and effect validated in time series with some kind of structural constraint. And the idea is because even if you look at this temporal correlation plus the statistical way of reconstructing with some kind of autoregressor with time series, there must be some underlying structure that is connecting everything. So it's not just that you define functional connectivity from effective connectivity from functional data, but there must be some influence of the structure, which has been mentioned many times, even in other fields, like that there is a relationship between function and structure. I think recently there was even a science paper that was mapping function from structure and structure from function. I've seen it from Amy Kuczynski was recently trying to. So it's in this direction works. And substantially, in the way I was doing it is that this is the traditional way how you use Granger, so that you have a time series and you try to reconstruct it from the previous time point using some autoregressor. Why the way I was using it was kind of making this reconstruction from the autoregressor with this other constraint matrix B. So the functional part will be this xt, and then this structural constraint will be from this matrix B, which I was using like defining some kind of overall error, reinforcing at each iteration of this error the structural constraint. And this, like, I could develop like in some kind of way, try to minimize this error and do it some gradient descent, and I could use it. Although this is still the oldest thing, and but it will also be expanded also for indirect connections, like from one region to another one, because I can merge together many constraints. And also, so I had some practical consideration, which I noticed that was working not so well with we were working with the bolt signal, but if I was doing the deconvolution with the hemodynamics was working better. So also my kind of impressions that with the EEG it's possible to achieve better results than fMRI because of the temporal resolution. And another thing that I noticed when we do this kind of merging structural function is that sometimes the atlas don't help us a lot, because generally when we look at activity in the functional are in the sum of the neuron, which is like the more external part of the cortex, while when we look at structural connections generally are in the white matter. So sometimes you need to tune the parameters, otherwise you might have issues that the tracks don't reach the area of the functional atlas. So this is one of the practical consideration I learned on time. But anyway, this was the oldest way of representing this structural constraint, and it helped a bit for classifications, but was like the old approach was just making a constrained version of the Granger causality. In moving a bit of the topic I wanted to talk to you today, so is that we moved a bit further. So we, instead of just the Granger causality, we use something that is a bit more advanced, that's called the Sugihara causality, which I have some videos from Sugihara that maybe can help. Oh, my screen. Are you still seeing my screen?
Yes, I can see your screen.
Yeah. So I summarize this, but I show you the video from Sugihara because it's probably better. So the idea is that they don't think like Granger that you have this temporal correlation, but they consider that data lies in some kind of manifold. And if you look at if you have something that you can see from the effect that helps you to reconstruct the cause, then there is some kind of causal relationship. I maybe show you from the videos from Sugihara, because like this seems a bit abstract. Okay. Yeah, from here. So these are, for example, 3 time series, like 3 brain regions, and actually they are the delayed version of the first one, and then the double delay of the other one. So this is the same, and this is a bit delayed. And it was its way of considering that you can see this, you can have some time series that mapped in a space where you have from the X one time series, on the Y the other time series, on the Z the other time series, that start resembling the Lorentz attractor, although Lorentz attractor generally is defined with the differential equation, but he kind of constructed in his simulation that you can have this substantially the 3 time series that are related to each other. They kind of define a dynamical system that is it might resemble like the Lorentz attractor. So the idea is that you not only have the manifold that is like high-level manifold that is telling the entire story, but you might have like a version where it's doing you do some kind of dimensionality reduction from one of the variables. I have to open the other video because yes. So from the original manifold defined by this all time series together, you have like a shadow manifold for one specific variable. And then we can have also another manifold for another variable, which I mean can be not necessarily has to be a variable, can also be the same thing but translated in time. And the way how this thing called convergent cross mapping was working is that then from the neighborhood of one shadow manifold, if you can reconstruct the other neighborhood, it means there is a causal relationship. It seems a very complicated way, but it's just a way in the end to have something that is more non-linear than just Granger. So these are the neighborhood of one manifold and the other one. And this is supposed to kind of, if you are able to make a reconstruction from a neighborhood of the other neighborhood, which represented translated in time, there might be some kind of causality. It seems a bit exotic for people who have never seen Lorentz attractor, but actually it was they show in some works that was working better than Granger, mostly because this thing is probably catching. It's probably very good to catch nonlinearity in this kind of temporal relationship. But of course, this was their work. What we and I mean, you can find it's actually a very old paper from Sugihara. So what we instead introduced is, first of all, we kept this view that you look at the effect. If you can reconstruct from the effect the cause, so there is a causal relationship, although it's more like a design. But we thought about some other ways of that are not that complicated as using the shadow manifold in this kind of representation from Sugihara, but still looking to nonlinearity between one time series and the prediction. And what we used was something called reservoir computing, which is something of special type of recurrent neural networks, although is if you never seen it, it's not just a recurrent neural networks where we train inside all the connections between the nodes, but we just have something inside that is called reservoir, that are nodes that are randomly connected, and they are never optimized. So there is like an initial layer of W of neurons that are simply something that allow us to map a time series to the reservoir. Then there is the reservoir, this randomly connected neurons, and then there is another layer which is doing the mapping back time series. And the only thing that is optimized is this last layer. The reason why we have these crazy things of connection is simply to have some kind of high level mapping to higher dimensionality, to higher dimensions of our input. So it's just making things more complicated to allow us then predict better. I don't know if for you makes sense so far, or I've been too fast.
People, if they have a question, they will share it on the in the chat, and I will share it with you. But so far, I think everything sounds clear. Thank you.
Okay, I'm not going too fast. Okay, good.
No. Thank you.
So substantially, with this we define our own alternative way without doing that complicated, let's say, Lorentz attractor story from Sugihara. We wanted to do something more fancier than just linear Granger causality, to something non-linear. And this is how we use it, like using something, using this reservoir computing, which also was not invented by us. We thought was a good way to employ it and to get some kind of nonlinear mapping of to predict time series. And the first thing we tried was some data from the Human Connectome project, from using the default mode networks, where we know that there was some directionality from the medial prefrontal cortex to the posterior cingulate cortex, and this was just a proof of concept. And then we tried it about some stroke data that we got it from Professor Cobetta. And the reason why we were interested in these things related to stroke is, well, first of all, because it's one of the still leading cause of mortality around the world. So it's still a clinically relevant topic. But also we found it was interesting because the connectome, the human brain connectome is something complicated, and we thought about this to use this effective connectivity, not just because we like complicated things, but because this effective connectivity can be seen as a way that the activity on one brain region is like literally transferring information in another brain region. And if you have stroke, a lot of these connections are destroyed. So some of these communications between dynamics within the brain are disrupted. So looking at stroke can be a good case study to see if there is anything useful in this story of effective connectivity, or is just a mental exercise to make things complicated. So we devised like an entire pipeline. Of course, we were initially interested to see the individual impact of the stroke, because the damage of the stroke more or less are heterogeneous. So someone can have, let's say, stroke more close to the Broca area. Someone can have stroke in another part of the brain. So each patient having a stroke is a case on his own. But there are also, is not the truth. So if you see, there are some works from people that shot strokes tend to be, there can be like a map of probability where the stroke is happening. So it's not that it's happening everywhere. It's not that heterogeneous. There is some kind of pattern where the stroke is happening. The thing that can make things heterogeneous, and I will go back there, is if it's happening on the left hemisphere or right hemisphere. That might complicate things if you want a black box where you are analyzing every kind of strokes. But if we don't consider that, we can assume that there is a general pattern where the stroke is happening. Also because when we see the disability, people have more or less the same disability. Like they cannot move like one arm, or they are lopsided for like with their lips, or they cannot speak anymore. So it's not that there is heterogeneous, like, and we have 100 cases. Like there tend to be a series of patterns that are more or less common. So that's why we thought about we have to have some kind of classification of the effective, using effective connectivity, and then try to have some explainable AI where we were looking at the relevant connections that were popping up most of the time. So even if there was some heterogeneity, we were hoping to find some kind of common pattern. And that was the story why we ended up with this overall pipeline. So to have some collection of data, pre-processing, building the effective connectivity representations in using reservoir computing, but also more legacy approach, then doing the classification, and then trying to explain the features that were used in for the classification. So for classification, at that time we didn't want to use the graph attention network, and I think it was more a decision of the student. But of course, in other things we are trying more recently, we are looking at graph attention network. But there was just the normal architecture with the graph attention network that I have it here. I hope you can see it. And I think it was optimized with Van de Bie and was also compared with other classification. Just in reality, of course, a reviewer asked us to compare to other classifier, but we were not actually that much interested in classifying a stroke or non-stroke. Because I mean, if you want to classify someone as a stroke, I don't think you need this complicated pipeline. You can just maybe look at one MRI and normal T1, and it's telling you that there is a clear damage. So the fact that we are using a classification is not because we're interested in classification, but it's more like if we can analyze some relevant features. That's the reason. We are not that much interested in classification. Of course, then when we introduce the classification, the reviewer asks us, please also show us all the metrics compared to other approaches. So we had to do this to give more sense of the quantitative results, because we cannot just look at qualitative results saying, there is this disruption in this patient and so on. So the other method we considered was, of course, the Granger causality, which I mentioned at the beginning, and transfer entropy, which is another way of estimating effective connectivity, which is actually nonlinear. So by design, is supposed to catch more stuff than Granger. And these were the results which were not that fantastic. So the classification, the under the curve was, in the best of the case for us, was depending on some settings, was even Granger was even better. So it's not that, if the idea is to only consider the for a classification, of course, sometimes maybe you can just use Granger causality. But as I was saying, our goal was not to just have an optimal classification, because you can use something simpler probably with the better results. But we were just interested to have a more appropriate effective connectivity representation to get the features that helping us to understand what's going on. And looking at the features, actually, we found something interesting, because as was kind of expected, there were some, because we used then afterwards some Lime to analyze which connection were mostly used by the graphical convolutional networks, and they were a series of networks, but most of them, the area that were also connected to language. So it seems language and stroke is something very critical. And another thing that we noticed was also what I was saying, the lateralization story. So it depends, I don't know, this figure is very small, but maybe I have it. Okay, I tell you what this figure was trying to say is that depending of how many, so if you had the same side where you have your language, the stroke, where is your, because most of the people have it in the left side, if you had the stroke there, then there were more damage. So it seems that the side where the stroke is happening has a higher impact at level of overall destruction of the network and also of the disability of the subjects. So there is, in fact, we are not experts in lateralization, but if you look, there are people who spend their life only focusing on this story of lateralization, damage from left or right. So we kind of confirmed with this overall pipeline that that there is a meaning of if the damage is on the left or the right. I don't have it, it's not in this paper for causality, but if someone is interested, we did some analysis about the story of the lateralization with gradients in another paper, which I'm not going to talk about today because we don't have time. But we also confirmed with studying the gradients in stroke subjects that it seems that even with gradients, so something not that complicated as our effective connectivity representation, was also possible to see that there was more disruption in the gradients depending in which side of the brain the stroke was happening. Now, summarizing wider, what we still believe that the story of the effective connectivity is relevant because, like, apart the region we spot, there are a lot of current study efforts that, of course, we are just computational neuroscientists, so we are not doing these things. But I'm aware that there are works related to stem cells addressing specific part where the damage related to the stroke happened. And we want to speculate that maybe using something like effective connectivity, you can highlight where there are this disruption of, because you have the directionality where the information is going from one part of the radio to the other one, it might give some insight where to apply this stem cell treatment. Of course, this is like a perspective. I have no proof that there's really any impact of this, but I want to hope that maybe there is some usefulness in this view. Then another thing that I want to mention, because it's like currently what we are doing, but actually I'm swearing a lot with this. So because of course everybody is since a couple of years is crazy with the large language model, ChatGPT, and so on. So there are the equivalent of ChatGPT and LLMs with time series. So there are some models that already exist, like Chronos, Time GPT, Time FM. And the idea is, like, instead of predicting the like one word after the other, you predict how is a time series is going. And we actually investigated a bit also with our data, and some of these claim to be zero shot, and we tried it as a zero shot, but the reconstruction was kind of 1% better than the like autoregressor of Granger. So it was not that explosive. If you fine tune them, was more or less like 10% better. And of course we have tried to make it in a causal framework, but also I didn't get that anything much better than Granger causality, honestly. So I'm kind of currently a bit disappointed of using a time series foundation model, because it seems like you're using something complicated to getting more or less at the same point with Granger. But if someone has better experience and is working on this, I'm open-minded to collaboration or to hear from you. And the last thing, like maybe this is a bit of advertisement. I'm trying to put all these frameworks like transfer entropy, Granger causality, reservoir in an open source library. So if someone wants to like test it or let me know, or maybe wants to open some issues on help me grow these things, I will be happy if you want to test it and open some issues. Plus, I've been trying to see how to visualize, because it's not something super easy. I tried like putting this error in 3D, arrows between one brain region, or colorful, like the direction from one brain region to where it's supposed to going. Like the arrow, the white is the end of the arrow, and the blue is the tip of the arrow, or something like that. So anyway, if you want to test it, let me know if it's working, or if there are bugs, or if you have proposals, or if you want to help me. And yeah, summarizing, I hope I show something interesting. So the overall story is that we devised a way that we can use some kind of nonlinear effective connectivity that is a bit more advanced than Granger causality. And we thought that even though if you want to see it as a classification, is not that the results are not that fantastic, but we never claim it. This is the ideal way to classify stroke. But we think is a good way to maybe spot some disruption within a specific stroke patient that might give some hint to where to do some stem cell therapy. And this is the reference. Yeah, and I thank you, and these are my contact if someone wants to reach out, or if you anything else.
Thank you so much.